everybody. Welcome to this the last plenary session. So we had a wonderful time with geometric science, and it seems that it's becoming more and more complex, going from parametric model to non-parametric model. So we move to something which is, I think, maybe simpler and maybe also quite complex. You will see that we have pretty pictures, so it will be a big change. So I think that we put this session about shape spaces because, okay, we believe that this is intimately related with geometric information, because the shape is something which is really carrying information, and we could say this is something on which we can act by just the shape is something which is carrying information and geometric information, because this is something you can deform more or less. Your shape is something you can act up with, say, diffeomorphisms. So this notion of shape and shape spaces is quite interesting because it's there is a question about how defining this shape spaces, and it's I think it's a geometrical question. It's geometry in finite dimensions, so it's I think it's a nice mathematical playground. Okay, the important thing is that we think that this could have some interesting applications. So I think it's a good place for people to work on. Okay, so we have four talks this morning, and we have another session this afternoon, which by Jean will be Gerig, which will be about more or less the statistical side. You'll see that we have a little bit about statistics at the end also. And okay, so people interested in should join the afternoon session. Okay, so the first speaker is James Fishbaugh from Utah University. He will talk about problem of geodesic, computing geodesic on some particular shape which are images. You can consider that images are shapes.
Hello everyone, I'm James from Utah, and this work is done under the supervision of my collaborator Stanley Durrleman here in Paris, and I'm from the University of Utah. And so yeah, I'd like to talk about sparse geodesic image regression framework today. So first, the question, what is image regression? So consider we have some observations, and usually in my work, these are medical images, say MRI, so 3D volumetric images. So in this case, we have observations of a child at 6, 12, and 18 months old. And we want to infer the continuous trajectory or estimate a model that best explains these observations. So in this case, we can generate a sequence of images which can be viewed as a movie. So now we have more or less a continuous evolution or a continuous growth model that in a least square sense best approximates the observations. So besides generating movies and pretty pictures, why would we do image regression, or why would we consider this an interesting problem? Well, for several reasons. It can potentially improve our understanding of normal or even pathological changes of brains or other anatomical structures. Mostly I focus on brains. It's really useful for alignment. Say, for example, aligning images with cognitive measures or cognitive scores that weren't acquired at the same time. So a child could come in for a scan at 6 months and for a cognitive test at 9 months. We'd like to align these two measures, or to align images from subjects, different subjects scanned at different times. And finally, with these image regression models, we can hopefully do some extrapolation for change prediction. So what's going to happen outside of our observation time. So there's been work done. There's been some work done in the past on image regression. Some methods to extend kernel regression to images, as well as some geodesic regression for images, which extend linear regression to images. And the main point behind these models is that they require to store many model parameters on the order of the number of voxels in the image. And for 3D medical images, this can be a very large number in the millions. And our motivation is that image change, the dynamics of image change can actually be described by a lot fewer than millions of parameters, and that these parameters should actually be located and concentrated in areas where the dynamic changes in the images are occurring. So this motivates the need for sparse representation, whereas the parameters of the methods before are connected to the voxels of the images. We want fewer parameters, reflecting the complexity of the changes rather than the sampling or the representation of the data. And this has the potential to improve the statistical analysis because there's less noise in the description with fewer parameters, potentially. And finally, we want these parameters to make sense with their spatial location. So they should be concentrated in areas that are changing the most, and in that sense, they might localize potential biomarkers for understanding brain development or disease progression or something of that nature. So today we present a geodesic image regression framework, which can be thought of as the extension of simple linear regression to images. So we want to estimate here a cost function or a criterion describing image regression, which is a function of I0, a baseline image, which can be thought of as an intercept with the analogy to linear regression. And then we want to estimate a continuous deformation of the ambient space, which changes our image over time to match our observations, and that can be thought of like a slope, with the, again with the analogy to linear regression. So there's sort of two terms in the criterion. There's a data matching term. So you want your deformed baseline image over time to match your observations. These are the actual MRI or medical images, and some additional trade-off between the regularity of the transformations. And here the deformations are parameterized as diffeomorphisms, which have a manifold representation. So the identity diffeomorphism is at the earliest time point, and then you follow a geodesic path on this manifold shooting from some tangent space representation to your final deformation. So in a more pictorial form, again, is the extension of linear regression to images. So we have observations in time, 01, 02, 03 here, and we consider the intercept, I0, the baseline image, and we also want to estimate the slope parameters, which here are denoted S0. It's a set of C0, the control points, which are these red dots, which are no longer fixed on the voxels of the image. They are located in space, and their position is optimized. And also these control points carry initial momenta, which act as the tangent vector representation for geodesic shooting. So these alpha 0 are what fully parameterize the geodesic. And every point on this line is actually a diffeomorphism, and then the action of that diffeomorphism on the image produces the actual evolution of the image itself. Okay, so let's sort of go into the pieces of the method one by one, and then I'll kind of summarize. Hopefully we'll all be on the same page when I get to the results section. So first thing is that the control points, C0, alpha 0, so these parameterize a continuous trajectory of control points and momenta by geodesic shooting. So by using these as initial conditions, by solving these coupled ODEs, we can compute the continuous trajectory of these control points and momenta. And it really just looks like a convolution with the kernel. So we take our C0, alpha 0, we shoot along the alpha 0 direction, and for each control point we get some sort of evolution and trajectory. Now the trajectory of these control points defines a dense flow of diffeomorphisms here at any time and any location in space, again by convolution. So now we have continuous C's and alphas that produces this sort of continuous dense transformation. Now, how do we apply this transformation to the images? Well, the action of a diffeomorphism on an image is actually the inverse transformation here. So by using the physical pixel coordinates y as initial conditions, So we have an image, we zoom in on a particular pixel. We don't consider its gray value here, but rather its physical coordinate, which is often defined by the MRI, or you can even use the indices of the image as the physical coordinate. You take that and it evolves in time according to this ordinary differential equation, using these pixel locations as initial conditions. So by solving this backwards in time, you can compute the trajectory of all your image pixels, which you can use to construct new images by simply interpolating those locations in the baseline image. So now we can construct a continuous sequence of images. So to summarize, you take your control points, which carry momentum vectors. You shoot along the geodesic equations. From there, you can define a dense flow of diffeomorphisms. Those can be applied to your image voxels by flowing them along the inverse deformation, and finally interpolation into the baseline image to create a moving image sequence. So that's sort of the machinery, and it shows that all we need to parameterize this system is a baseline image for the intercept and the control points and momenta, which act as the slope. And from there we can generate this whole sequence. So now we have a more specific criterion, now parameterized by the baseline image and the control points and momenta at 0. Again, it's a data matching term, which here is just like a sum of square differences of the intensities, the L2 norm on the images, and some regularity on the deformation. The regularity is measured as sort of the kinetic energy of these particles. And again, it's subject to those ODEs I showed before, one involving shooting the control points and the other flowing the image voxels along the inverse deformation, with the initial conditions of C0, alpha 0, and the voxel locations. So we want to solve this optimization problem, find a minimum of this cost function, sort of to, in a least squares sense, match our observations. So we think of this as a gradient descent type of solution. So we want to compute gradients. So first, with respect to control points and initial momenta, we end up with this equation where the gradient with respect to the control points and momenta is actually found by solving, again, a coupled system of ODEs. The first one involving data terms. So the gradient of the data term act as jump conditions at the time of observation. So you start at with initial condition 0 at the final time point in your evolution. You integrate these equations backwards in time, adding gradients at every observation. And then once you get back to 0, or the initial time point, you use that value to update the location of the control points and the momentum. And then for computing the gradient of the initial image, it's actually the sum of the gradient with respect to the data term, or with respect to I0 of the data term. And this is pretty simple. You just take your voxels and you flow them to the time point corresponding to the observation. You compute a residual between the observation and that transformed voxel. That gray value is then distributed in the image according to weights from interpolation. And then you sum this up for all the observations. So the gray values are then accumulated for all your observations. Okay, so we talked about earlier how we would like to parameterize this within a small number of parameters, which best describe image change over time. So we take the criterion we had before and now consider this sparsity penalty, which is an L1 norm on the momenta. So we prefer to have many zeros in our for our momenta. And this changes the optimization slightly. It's no longer a complex criterion. And we solve it with the fast iterative shrinkage thresholding algorithm, VISTA, which uses the gradient with respect to just the original criterion without the L1 penalty, and then undergoing some soft thresholding to reduce momenta in general and to zero out momenta with very small magnitude. And this type of sparsity prior has been used recently in the context of atlas building for images and shapes. Okay, so that's sort of guts of the method. Now let's talk about some experimental results. So let's consider this synthetic example in 2 dimensions, where we start from sort of a plus shape to sort of a flower, and this was generated by geodesic shooting from this shape along predefined initial momenta. So in some sense, this represents the best case scenario for our model, because this data actually follows a geodesic path, and our model is geodesic, so we should be able to recover this pretty well. And here the momenta were located at every pixel. Okay, so what we do here is we want to look at the impact that the sparsity has on the estimation, or on the model estimation. So here we're increasing the importance of sparsity in the optimization, and we see in general that the number of momenta and control point pairs decreases as we increase the sparsity parameter, and that they cluster around the areas that are changing the most. You can see here the highest sparsity value, they're clustered in the areas where the image changes the most. So we can look qualitatively in the form of an animation at each of the models for different sparsity parameters, and qualitatively I'd say they all look very similar. As you increase the sparsity parameter, you lose some details, but it's hard to see just with your eye. So we take more of a quantitative look at this. So what we see here is as we increase the sparsity parameter, the blue line shows you the way the control points change with an increase, and the green line shows you how much error you incur with respect to matching those observations. So the sparsity doesn't come for free. You do incur a small error, but we see that it's quite small. There's a whole range of sparsity values where you incur just a 2 to 4% relative error. In fact, if you're willing to incur 10% error in your data matching term, you can get this down to 67 control points from originally about 80,000. Okay, so let's look at another example. This with, again, 2D images, but from real medical images of a same child scanned at 6, 12, and 24 months old. And it's a little bit hard to see on the projector, but the contrast is pretty poor at 6 months and improves over time, and at 24 it's quite nice. So in this case, we want to estimate, we estimate the model starting from 24 months and go backwards. So again, we want to look at how sparsity impacts the model estimation. So again, we increase sparsity going to the right. And we see again the number of control points decreases as the sparsity parameter increases. And again, they cluster around the areas where the most dynamic or salient changes are occurring. In this case, when the sparsity parameter is very high, we are mostly capturing scale changes of the skull here, with very few parameters in the interior of the brain. So this can be argued as a both good and bad result. Good in the sense that we capture what is the most salient change, which is the scale, and argue that it's not great because we are missing potential important changes in the interior of the brain. So there are some potential ways to improve this I'll talk about maybe at the end of the talk. So again, we'll just look qualitatively, how do these models differ as the sparsity parameter changes? And qualitatively, I'd say they look very similar. I think our eyes mostly pick up the scale changes of the brain in this case. So it's really just scaling, and you can't see much interesting change happening in the interior of where the tissue develops. And again, we can look at the way sparsity impacts the number of control points as well as the amount of error that you incur for the sparsity. And here the picture is actually a little bit nicer. We have sort of an asymptotic behavior of the number of control points and sort of a linear increase in the relative error. So we can actually decrease the number of control points drastically for just 2% relative increase in the error with respect to matching the observations. So we go from a little over 45,000 parameters down to 47 here. Okay, so let's consider a 3D case here, which is, this is sort of cutting edge work for me, sort of work in progress. So, this is the same patient with Alzheimer's disease, scanned 4 times here over about a 2-year time window. And it's really hard to see from static images, but there are some ventricle growth. These black structures are fluid structures that increase in size as the important tissue surrounding it sort of atrophies. So it's not a good thing in brain development. So what we want to do here is we can look at what happens during the 2-year time window, but also, as I talked about earlier, we have the idea of extrapolation. So let's look at what happens beyond 2 years and predict what this subject's brain might look like over the next 4. So this is a total of 6 years. Sorry, this animation plays very slowly. So you kind of have to look at the ventricles here to see the changes. So the lateral ventricles, these black structures, are growing as the white tissue here atrophies. And just note that since this is a 3D image, there are over 2 million voxels, and our representation has just under 36,000 momenta, so 98% decrease in the model parameters. And you can see we still are able to model pretty interesting and realistic changes for this patient here. So to conclude, we introduced a new geodesic regression framework for images. The first sort of idea is that we decouple the deformation parameters from the image representation. So the control points are located in the ambient space that the image is embedded in, and their position and their location is optimized as part of the framework. So they're not tied to the voxels. They're actually free to move to the areas where they're most necessary. And finally, adding an additional L1 penalty to then select from those control points and momenta an optimal subset. And we did some experiments and showed that you can reduce the number of parameters with only a minimal cost. In these experiments I've shown in terms of matching your target data, in terms of matching the observations. So in the future, there's some things we can do to maybe improve this model. We can consider using kernels at multiple scales. This might help obtain some more interesting deformations in the interior of the brain in the pediatric example. We might also consider image metrics that are less sensitive to contrast and intensities, and that could help, help with things happening in the interior of the brain where the contrast is not so good, not as strong as the edge of the skull, for example. And then finally, the ultimate goal is to actually integrate this kind of model with a framework for doing longitudinal analysis, so for doing statistics on different groups in a longitudinal study. So I'd like to acknowledge the funding sources that made this research possible, and thank you very much for your attention.